this video, we are going to talk about buffers. So a buffer is a solution that can resist a change in pH when an acid or base is added to the buffer solution. Now, a buffer is going to be made of a weak acid and its conjugate base, or it can be made of a weak base and its conjugate acid. So if we look at an example, we could have something like hydrofluoric acid and fluoride. That could make up a weak base or a buffer because it's made up of a weak acid and its conjugate base. You could have something like acetic acid and acetate. Now, something that can be really difficult for people is that ions do not exist by themselves. So I cannot go and find fluoride in the stockroom. I cannot go and find acetate in the stockroom. So these anions do not exist by themselves. They exist as soluble ionic compounds. So if I were to go into the stockroom, I would have to find something like sodium fluoride or lithium fluoride or sodium acetate. You could do lithium acetate, you could do potassium acetate. And these are all examples of soluble solids at room temperature. Now, we could also have an example like ammonia and ammonium. Again, this is a cation, so this is an example of a weak base and its conjugate acid. Ammonium does not exist by itself, right? Cations do not exist by themselves. So you would have to go to the stockroom and get something like ammonium chloride or ammonium fluoride, ammonium bromide. You really don't want to use a counterion that has a conjugate base of a weak acid. When you add the sodium, lithium, or potassium, or chlorine, chloride, bromide, those are called counterions. So you have to make sure that you are getting those counterions in there. So let's look at how a buffer works. So if we look at our hydrofluoric acid buffer example, we have HF plus water dissociates partially into hydronium ion plus fluoride. So if you have a strong acid that is added, like HCl, remember it completely dissociates into hydronium ion. And so that hydronium ion can react with fluoride and it gets neutralized. If you have a strong base that is added, something like hydroxide, then the hydroxide reacts with the acid, HF, and gets neutralized. Now, why this has to be made of a weak acid or a weak base and its conjugate base and conjugate acid respectively is because it exists in equilibrium. And so when you start off with this buffer, you have to make sure that you have the addition of that conjugate base because the addition of the conjugate base drives the reaction, it drives that equilibrium to the reactants. And so we will have more acid in solution. And as the acid gets neutralized by reacting with the fluoride, it is going to yield hydrofluoric acid, which is part of our equilibrium system. As the hydroxide gets neutralized, it's going to form fluoride, which is also part of our equilibrium system. So let's look at calculating the pH of a buffer. Now, before we get into the calculations, you have to realize that buffers are not going to work indefinitely. And so we have something that is called the buffer capacity. So the buffer capacity is generally talking about the strength of the buffer. And you can see it referred to as the ability to maintain the pH after the addition of an acid or a base. Now, there are two things that really can contribute to the buffer capacity. The first is the higher the concentration of the buffer components, that is going to result in an increase in capacity. The second is going to be the closer the concentrations of the buffer components are to each other, that is also going to increase your capacity. So for example, if the concentration of my acid is 0.1, then if I have a concentration of my conjugate base also equal to 0.1, that is going to increase the buffer capacity. Now we can calculate the pH of a buffer using what is called the Henderson-Hasselbalch equation. So if we look at the chemical equation of a generic acid dissociating in water, then it will dissociate into hydronium ion and its conjugate base. Now I can come up with the equilibrium expression for this process. It's going to be equal to the concentration of hydronium ion times the conjugate base divided by our acid. So the concentration of our acid, if we rearrange that, is going to be equal to Ka times the concentration, I should write this as our hydronium ion, not just leave it as the acid. So it's going to be equal to Ka times the concentration of our acid divided by the concentration of our conjugate base. Now, if we want to express this in terms of pH, then I can just take the negative log of all of this. So if I take the negative log of my hydronium ion, that is going to give me the pH. And we will get the negative log of Ka minus the log of my acid over my conjugate base. So this gives me the mathematical equation pH is equal to pKa plus the log of the conjugate base over acid. Notice that these two switched when we went down to the equation. That's why we changed that to a plus. And this right here is known as the Henderson-Hasselbalch equation. Now, keep in mind this is very, very important. This is only used for buffers. You cannot use it whenever you want to. It's only when you have concentrations of both your acid and conjugate base in solution. So let's look at an example of how we can use this. What is the pH of a buffer solution if 0.1 molar hydrofluoric acid is mixed with 0.1 molar sodium fluoride? Now, something you need to remember is that sodium fluoride is completely soluble in water. And this sodium ion right here is only going to be a spectator ion. It's only going to be watching the chemistry taking place. It's not going to be doing any of the chemistry. So what that means is we don't really care about it. We only care about the fluoride. So the first thing I need to do is look up my Ka for hydrofluoric acid, which is 7.2 times 10 to the negative 4. So I can use the Henderson-Hasselbalch equation to solve for the pH of this solution, but before I can do that, I need to calculate the pKa. So that is going to be equal to the negative log of 7.2 times 10 to the negative 4, which gives me 3.14. So now I can plug that into my Henderson-Hasselbalch equation. pH is equal to 3.14 plus the log of 0.1 over 0.1, and that gives me a pH equal to 3.14. Remember, the log of 1 is equal to 0. So what this tells us is that if the concentrations of the buffer components are equal, then your pH is going to be equal to your pKa. And the closer your pKa is to your desired pH, the better your buffer capacity will be. So when you're choosing an acid to make a buffer, you want to choose a weak acid or weak base that has a pKa or pKb that is closest to the desired pH.